Okay, so we can move now to the next session, theory, to change a little bit. Please.
Okay, so then, no? Thanks. Good, so then let us start with the theory session. The first talk will be given by Darrick Chang, and he's from the Institute of Photonic Sciences in Barcelona, near Barcelona, and his talk is on realizing many-body complexity in quantum optics.
Okay. Well, so first, thanks a lot to Kyle for organizing this conference and for the opportunity to be here and hear all these amazing talks. So my talk is not about kind of nanophotonics and atoms per se, although I hope that some of the themes that I'll be talking about will nonetheless resonate very closely. So first, I just want to acknowledge my group, especially Charlie, Mark and Boise, who did most of the work that I'll be talking about today. Mark is here in the audience. And so maybe just to kind of set the context a little bit, I think there's kind of two distinct limits of cavity QED in which many of the people in the field work. So one is kind of single atom cavity QED. So I think people would say that in principle this system is very quantum. It's a single two-level system. It's very anharmonic. In principle, we know that if the system works well enough, we can build quantum computers and so on. The kind of challenge, though, is that to really do that at scale, you need very, very high interaction efficiencies or high cooperativities that we don't really know how to get to yet. So one way to kind of increase efficiency of atom-light interactions is then to use many atoms. So this underlies a lot of the physics of collective enhancement, spin squeezing, superradiance, et cetera. But then, one of the kind of trade-offs is that, the price you pay for getting this high efficiency is that because light kind of mediates all-to-all interactions, the underlying theory tends towards kind of large spin or mean field theory. So you maybe lose a little bit the complexity of quantum mechanics in general. So one theme that I've really been occupied about in the past few years is to really think about in atom-light interactions, are there realistic ways that we can achieve richer forms of quantum many-body complexity? And I think there's kind of two general themes that we explore a lot in the group. So one is simply how do we kind of create smaller dissipation in atom-light interfaces? So in traditional theory, it's assumed that when you have an excited atom, it's going to emit light into 4 pi, so into directions that you can't collect, at a rate that's just kind of fixed. So it doesn't depend on any other atoms, et cetera. But that actually is not consistent with wave interference. So wave interference says that actually it's the correlations or interference between all the atoms that matters. And so one thing we've been thinking a lot about is if we can somehow use like very dense, let's say even ordered arrays of atoms where interference effects are enhanced, then maybe we can take the kind of light being emitted into 4 pi and destructively interfere it away. And so for simple applications like quantum memories or photon gates, we know that that actually leads in principle to even exponential improvements in the errors as a function of things like cooperativity or optical depth. More recently, we're thinking about how to encode many-body effects into these kind of destructive interference or subradiant manifolds. So here I won't have time to talk about that theme, but there's a kind of another theme which I think is quite important if you want to achieve many-body complexity, which is in atom-light interactions, atom-light interfaces, how do you systematically evade mean field behavior? So I guess there's this kind of loose connection or maybe urban myth in physics that when you have long-range interactions or simply high connectivity between different spins, between different sites, that tends towards a mean field description. And in some cases, you can make that statement very precise, but in a lot of other relevant cases, it really is just kind of a general belief. So one thing that we've tried to do a lot in the group is to really systematically understand when that's true and when it's not, are there parameter regimes where I can prove that something is going to be mean fieldish? And what does mean field actually mean in a precise way? And conversely, are there systematic paradigms we can find, even though we have long-range interactions, for us to evade mean field behavior and thereby hopefully get something that's more complex? And so in this talk, I'll try to give you a flavor of one of the problems that we're thinking about, which is that when you have strong, long-range interactions, even all-to-all permutation invariant, are there little things that you can do to tweak the system? So all of a sudden, you go from long-range interactions to emergent locality, to emergent short-range interactions. And one kind of particular phenomenon that we want to explore or to realize with this effect is something called a quantum spin liquid. So it's an exotic state of quantum matter. So maybe first I'll just give an introduction to quantum spin liquids, because it's not necessarily a topic that people in quantum optics are very familiar with. So the paradigmatic system where quantum spin liquids probably exist in real life are kind of anti-ferromagnetic Heisenberg models, which are frustrated. So let me kind of break down those ideas a little bit. So let's just start with kind of unfrustrated models. So a simple example could just be like a Heisenberg anti-ferromagnetic model on a square lattice. So you have spins that are living on the vertices of this lattice, and they interact with nearest neighbors. And then if you have just two spins, then what they want to do is they want to anti-align. So just from kind of classical intuition, it's kind of easy to guess what a ground state might look like. It's just one where kind of alternating spins are pointing up and down. So that's a classical picture. It's not an eigenstate of the full quantum Hamiltonian, simply because of quantum fluctuations in the Hamiltonian, or rather product states. You can't use product states to diagonalize all the different components of that spin interaction at once. But nonetheless, what people know is that even though that's not the true quantum ground state, this cartoon picture basically encodes many of the key properties of the quantum ground state. In particular, the quantum ground state does exhibit a kind of spontaneous symmetry breaking, so the ground state has a lower symmetry than the original rotation invariant Hamiltonian. And it does exhibit this kind of long-range spin ordering. So a more challenging case is once you start making the system frustrated. So instead of just having, let's say, nearest neighbor interactions that want to anti-align, you also add next nearest neighbor interactions. So in this case, the blue, so along the diagonals, which also want to make spins anti-align. And then if you just start trying to use classical intuition to guess a ground state, you see it's actually pretty hard because, for example, I can take one spin and point it up, a second spin and point it down. But then on the third side, I can't really decide whether I should align according to the red lines or according to the blue. Okay? So the fact that it's kind of hard to kind of guess the properties from a classical sense might suggest that maybe actually the true quantum ground state is a lot more exotic. Maybe the system doesn't order at all. So maybe there's no spontaneous symmetry breaking. And maybe the order, whatever it is some kind of more exotic quantum order. Okay? It turns out that that's almost certainly true. So that almost kind of defines a quantum spin liquid. In the next 2 or 3 slides, I'll actually go on a bit of a tangent. So it'll be a little bit mathematically opaque. But I hope by the end there's a kind of punchline, and I hope it gives you a kind of new appreciation of why quantum spin liquids are so cool. Okay. So some hardcore condensed matter theorists got interested in this kind of problem 30, 40 years ago, and they started throwing some pretty heavy mathematical machinery at this problem. Okay. So one thing they did is they started using kind of path integral methods, and it's just a kind of technicality. But if you want to use path integrals, it's much easier to work with bosons or fermions than with spin. So the first thing you want to do, if you want to use these kind of mathematical tools, is you can say, for example, instead of talking about spins, I'm going to think about the system as being fermions. And so at a given site I can have either 0 fermions, I can have a spin up fermion, a spin down fermion, or 2 fermions. But then, of course, the physical Hilbert space is that I have a spin. Okay, so I've added extra degrees of freedom that aren't there in the physical problem. Just a kind of technicality, if I start writing this kind of spin Hamiltonian in terms of fermion operators, creation and annihilation operators, a single spin operator becomes quadratic in fermions. So then a spin model, like a Heisenberg model, becomes quartic. So it's a kind of interacting fermionic theory, and that's not easy to solve in practice. So the fact that you have a kind of constraint, the fact that your physical Hilbert space is smaller than your kind of mathematical one, almost by definition, that makes the theory a gauge theory. So for example, one thing you can write down is a physical constraint. For example, the total number of fermions on a given site has to equal 1. I have to either spin up or spin down. And that kind of expression on the left-hand side is an operator expression. I know it's 0 for my physical space. So then if I start defining fancy local operators, e to the I something times g, I know that g is 0 for my physical space. So on my physical Hilbert space, these operations don't do anything. But by unphysical space, they start transforming the things around. And so that's exactly a kind of local gauge transformation or some kind of redundancy that's built into my system. So again, if I have a quartic Hamiltonian, that's too complicated to solve. So then people started throwing more mathematical tricks. So one thing you can say is if I have a direct interaction between fermions, I can always introduce a new degree of freedom, some kind of boson that mediates the interaction. So that's this kind of field U. And what that does simply mathematically is you change from a kind of quartic Hamiltonian to a Hamiltonian that's cubic. Okay, so it's quartic in the fermions times linear in the bosons. And then because my original theory had this redundancy, because it was a gauge theory, essentially that kind of gauge redundancy is also inherited by this new model. So actually this bosonic field becomes a bosonic gauge field. So I formally mapped my theory to a lattice gauge theory. Now, of course, interacting lattice gauge theories are still too complicated to solve. So then you can go even further. You can say, well, let's just kind of hope that maybe our gauge fields or operators can be replaced by numbers. So it's kind of some kind of fancy mean field theory. So at the end of all that kind of math, you get down to some kind of non-interacting fermionic theory that you can solve. You can try to construct spin correlations, et cetera. Okay, so now if you're not familiar with this theory or you don't know the punchline yet, you should rightfully complain, right? Because I've taken this kind of seemingly innocent spin model and I've dressed it up in this kind of fancy, ridiculous language of lattice gauge theories and fermions and so on. So you might ask, is that kind of just physically fake nonsense? And if you want to make that kind of protest a little bit more precise, well, in the original spin model, I have this kind of rotational invariance. So I know that total angular momentum of the system and its projection along z are good quantum numbers, and they should be integers, right? But on the other hand, if I literally believe this kind of quadratic fermionic theory, then I should conclude that my fundamental excitations actually carry half integer spin, and moreover, they obey fermionic statistics. So I can have two excitations living in different parts of the medium, and if they kind of exchange, they should pick up a -1. Okay, and those kind of two concepts are not easy to reconcile with one another. So then it turns out that simply this kind of mean field approximation, and when you go to fermions and so on and make this mean field approximation, it's just too naive. And the reason it's naive is that when you have gauge fields, so basically kind of photons, they're generically massless, they propagate long distances. And so they'll mediate long-range interactions between the fermions. And generically what happens is those long-range interactions are going to glue my fermions back together. So now I get bosonic particles with integer spin again. Okay? So then the conclusion of all of this kind of math is that, forget about it, it's just nonsense. Okay? But then, Xiaogang Wen in the early 2000s came around and said, well, not so fast. So we know from high energy physics that we can have something like a Higgs mechanism where gauge fields become massive. And then if that happens, then all of a sudden they can no longer mediate long-range interactions between the fermions. Okay, so then I would have to conclude that this kind of mathematical trickery that I was talking about here, if this kind of if this Higgs mechanism turns on, then actually these kind of fermions that I introduced first just mathematically actually become real objects in my system. My fundamental excitations do indeed carry half integer spin and do have fermionic statistics. And moreover, these kind of gauge fields that I also introduced just by trickery at first also become real. So now all of a sudden I have a spin system where the fundamental physics, the low energy physics, looks more like the physics of the universe, of the standard model. Because the standard model, of course, is just kind of fermions and gauge fields. So to me, it's one of the most beautiful examples of emergence in physics. I can take one system, I can get completely different physics, and so I never know what's fundamental anymore. Any effect can come from any other effects. Okay? And so to me, that's what makes kind of spin liquids and emergent phenomena so interesting to study. Okay, so that was kind of a big picture introduction of spin liquids, but there's kind of one important thing that this analysis also, which also comes out of this analysis. So people don't really know exactly the kind of wave function of these spin liquids, but by various approaches, they have a kind of pretty good cartoon guess. And those, the many-body wave function looks like these kind of RVB spin liquid states. So in this kind of cartoon, what you do is you say, I have a collection of spins, and I'm just going to say that any one spin is guaranteed to pair up with some other nearby spin and form a singlet state. Okay? So if I only draw one kind of cartoon picture like that, like this one here, obviously that cartoon breaks all the kind of translational rotational symmetry of the system. But then what's believed is that the spin liquid ground state is actually just a massive superposition of all those cartoons. And that massive superposition actually restores all the symmetries of the system. So now my kind of ground state doesn't break any symmetry. I have no spontaneous symmetry breaking. I need some other, and that's kind of some hint that you need some other paradigm to describe this type of phase. So some kind of more exotic quantum order, or these days the word is topological order. Okay, so how might we kind of get that physics from cavity QED? So I'll just consider the most minimal model of cavity QED, which is atoms interacting in a permutation invariant way with a single cavity mode. And when the cavity is off resonant, then it's pretty well known that what the cavity does is it mediates all-to-all spin interactions. So any spin j can flip down by physically emitting a photon. Any other spin I can flip up by absorbing that photon. And because this Hamiltonian has no notion of space or geometry, you can rewrite the Hamiltonian purely in terms of collective or total angular momentum operators, s squared minus sc squared. So that's this kind of famous spin squeezing or one-axis twisting Hamiltonian in quantum optics. So it's actually the poster child for collective spin interactions. But then I said one of my goals is to evade spin or collective spin or mean field physics from the very beginning. Okay. So this model, indeed, if we start with, let's say, all spins pointing down, or all spins pointing up, it describes spin squeezing, Dicke superradiance. There is indeed some kind of large spin description for that. But what we can do instead is, in quantum optics, we're free to choose the sign of the interaction. So I can choose T to be positive. In that case, my ground state manifold is actually S equals 0. So it's a global singlet state with no angular momentum. And if I have no macroscopic spin, then I have no macroscopic spin description. Everything is quantum fluctuations. Okay? And you can ask, well, what are the basis states that make up S equals 0? Well, it's any way that you can pair atoms together into singlets. So it includes this kind of quantum spin liquid wave function that I described. It also includes kind of things like valence bond solids and just kind of completely arbitrary pairings. So now what we want to do is we want to try and pull out. So S equals 0 is massively degenerate. There's interesting states in there and states which are not. And then what we want to do is kind of pull out the interesting states or separate them energetically from the ones that are not. And you can kind of take inspiration from Michelangelo. So supposedly he said that he never carved David. He just took the marble and kind of chipped it away at everything that was not David. Okay? And so in quantum mechanics, what we can do is we can take our cavity Hamiltonian, which is very strong, and just add a little bit of a perturbation. And that's going to kind of generically break up this degeneracy. So if we do it correctly, maybe we get out as the true ground state a quantum spin liquid. So one kind of practical way to do that is maybe to add some kind of short-range Rydberg or Ising interactions into the story. That's a kind of timely idea because there's a number of groups which are trying to build such systems now. So I won't really go into the details of the physics, but maybe just to kind of illustrate the cartoon picture. The idea is like, first what you do is you just create a kind of classical Ising interaction. So this is a classical magnet. It's ordered. And then the idea is that when you turn on these kind of strong cavity interactions, the cavity fluctuations are going to melt that classical order into a quantum spin liquid. So you'll have to kind of take my word that it's true, or I'd be happy to kind of describe more of the physics after the talk, but essentially, hopefully that gives you an idea of some of the physics that we're looking at now. So again, I think in quantum optics, how to realize many-body complexity is an open challenge, but I think we're starting to find interesting paradigms where we can kind of evade mean field behavior and kind of suppress strong dissipation by using subradiance. So thank you.
Thank you very much for the talk. The paper is open for discussion. Yes.
Maybe just towards the end, a very simple practical question. So how many individual atoms in such a tweezer array in the cavity would you need to really be in this interesting many-body regime?
Yeah, so that's not an easy question to answer, in part because, I think for these types of spin liquids, they say Z2 spin liquids, I guess there's not really a kind of smoking gun yet of, okay, here's something that I can measure. I mean, I guess what you ideally like to see is I want to directly exchange two particles and see a kind of anionic phase, right? Or I want to measure some kind of topological entanglement entropy. So the problem with that is they're pretty, no one really knows how to do that. So you can look for kind of weaker signatures, but yeah, it's not a smoking gun. So I would say kind of 10 by 10, maybe, but again, these it's a little bit hard to say. Here's a smoking gun that I know how to measure.
Okay. More questions? So for a mortal experimentalist, when you say if interaction gets long range, then the prediction is that it can be described by mean field. And you say, but that's not always the case. Can I naively imagine that you can construct such a state which violates this by actually adding one particle at a time in such a way that there is destructive interference? So can I start by taking two particles and having a subradiant state and go on?
Probably. So yeah. So that almost sounds like, so if I can start turning on, that's almost like turning on long range interactions, but in a kind of local way. Mm-hmm. So yeah, it's quite possible that evades mean fields. But yeah, I think the general challenge is it's very what we're really trying to do is really trying to make those slices precise, right? To say, okay, if you do this in a lab, you will be mean field. And if you do this, you will not. So maybe one example is kind of superradiance, when you have multi-mode superradiance, can we prove that that's mean field in some sense and under a certain regime? So that's a problem that I think maybe that's kind of closer to experiments, but that's a kind of very relevant question where we're trying to kind of, play with the math and understand how to use the mathematical technology to prove statements like that.
Okay, thanks. So I see no more urgent questions. Then let's thank Darrick again. And we come to the second talk of this theory session, which is given by Saverio Pascazio from the University of Bari. And he will report on dynamics and dissipation in waveguide quantum electrodynamics.
Okay. So first of all, let me thank you for inviting me here, Takao in particular. It's a great pleasure to be back. I used to live in Brussels many, many years ago. And today, as my chairperson was telling you, I will talk about dynamics and dissipation in waveguide QED. And now this is a work that I've been doing during the last 10 or 15 years in collaboration with a number of people. There is a poster by Rosa Capurso in the poster session, so if you're interested, just go and have a look at it. So I will be talking about one-dimensional systems. Let me tell you, before I even started, a few years ago, I didn't find one-dimensional system interesting enough to be studied. And I changed my mind for a number of reasons. I will give you maybe a couple of reasons as I go on during my talk. They're very interesting, essentially, because you can simulate things that you cannot do in 2- and 3-dimensional field theories. So, and this enables you to look at the things, to look at the phenomena from a different perspective. Okay, so I will focus on 2-level atoms in a waveguide. So essentially I have a waveguide and I have 2-level atoms. So, and I will be working the rotating wave approximation. So things are rather elementary from this point of view, just 2-level atoms and rotating wave approximation. And this is, you know, what I will be looking at. I mean, oh, it doesn't work. So a system in which you see photons propagate from one atom to the next one. Okay, now one of the reasons why I thought that this system is interesting, it's because of a paper by Peter Zoller, which is already maybe, I don't know, 15 years old, in which he looked at a waveguide and he put a mirror at the end of the waveguide. And essentially, depending on the distance between the atom and the mirror, the emission can be hindered or enhanced. I mean, it is hindered if you look at this, in this case, and it's enhanced in this case. So you can have an emission which is hindered if the system resonates with, if the photon that is emitted resonates with the mirror. And of course, I use a semi-classical language because there is no photon being emitted. It's just the amplitude for the photon being emitted, reflected by the mirror, and going back to the position of the atom. Now, it's very easy to look at the Fermi-Golden rule, so the decay probability. And the decay probability is that interesting dependence, the sinus square of KL. L is the distance of the atom to the mirror, and K is the wavelength of the atom. So when that sinus square resonates, you can have enhanced decay or suppressed decay. And so when I talk about hindered emission, it means that the system can be stable to a fairly good degree of approximation. Of course, let me say before I even start, you always have dissipation effects because the photon can be emitted outside the waveguide. I will be neglecting this. I will just take a Hamiltonian approach to the system. Okay, good. The first reason why I thought that these are very interesting is that I was at a talk by chance, a talk by Per Delsing already 10 years ago. And Delsing was showing this very interesting experiment in which you have an artificial atom in front of a mirror. The mirror is shunted to somewhere. So you have the photon that propagates along the serpentine this way. Okay. And you feed the photon through this port. So the photon arrives on the atom, and if it goes through the atom, it can be trapped in the serpentine. Okay, and as I told you before, it can be trapped in different ways, depending on whether the wavelength resonates with the distance from the mirror or not. Okay, the title of the paper is interesting, is probing the quantum vacuum with an artificial atom in front of a mirror. That's the title of the paper. It's a Nature Physics 2015. Okay, what I found very beautiful is that for some distances, you see, when L over lambda becomes 1/2, essentially the atom, thank you, yeah, maybe it's a good idea. I noticed that I can fall down, sorry. You're not allowed to? Why? No, because it's going to create feedback with the other microphone. Oh, I see. So let me, I will try to speak in the microphone. Okay, so as you see, when you are in a situation of resonance, the atom disappears. So you see there are no the red points there are the measurements. So when the atom is at the correct distance from the mirror, the atom disappears. I used to show this slide when I go to high schools and give just talks to high school students, because this is these are the symptoms of decoherence. So when the quantum system becomes very difficult to address, the system disappears. It's very resilient against noise. At the same time, it is extremely difficult to reach. Okay, so you have to accept this dichotomy. Okay, so I found this very beautiful, that the atom disappears in front of a mirror. Spectroscopically, the atom is always there. It's an artificial atom. It's a few hundred microns, but it disappears when it resonates with a mirror. You cannot see it anymore. Okay, so let me give you another Hamiltonian. Now, I will work with two atoms just to start with. The two atoms are, this is the Hamiltonian. You have the two atoms. You have a free part. EA is the excited state of atom A, and EB is the excited state of atom B. Then you have the integral, that's the photon field. And then you have a coupling in the rotating wave approximation. You can see that here, sorry if I leave the microphone, when the atom is excited, you excite or you de-excite an atom and you create or kill a photon. And you can do this at a distance d. Okay, so there are the two atoms in the rotating wave approximation. You know everything about the system. You just have to solve it. And it's not difficult to solve. What is interesting is that the other atom acts like a dynamical mirror. There was a talk this morning, I think, by Julien, I'm not sure, in which, so the electric field of the photon that is going to be emitted is forced to vanish at the position of the other atom. So if it vanishes, then the two atoms resonate, the decay is hindered, and you basically trap a photon between the two atoms. This is a stable state. Is that a stable state in the sense of quantum mechanics, or it's not? Let me investigate this. Okay. Well, it is a stable state, because if you look at the red curve gives you approximately the energy of the field between the two atoms. So if the two atoms are at the right distance, the field energy distance is trapped between the two atoms. You have nothing outside. And also you can have excited state. For example, n equal 2 is an excited state in which the photon oscillates a couple of times between the two atoms. Now this picture is valid at the first order. When you perform a more detailed analysis, you see that there are always tails. The existence of tails is interesting because you see the atom forces the electric field to vanish there, more or less, the electric field like this. But then there is an evanescing tail, a tail outside the system. So this tail explores the part of space which is outside the system. This phenomenon is only possible in one dimension. In two dimensions, this phenomenon disappears, unfortunately. It was an old thing. It was considered when they studied quark confinement in QCD many, many years ago, 40 years ago. And it doesn't work in 3D. It only works in 1D. Okay. One technical word. I have to explain you what the technique I'm going to use, because I will abandon this technique in a minute. So the technique is the following one. You look at the evolution of the system. You prepare the system. There are for instance, two excited states, EA, EB, and you let it evolve under the action of the Hamiltonian. And the way you solve the system, you look at the resolvent. The resolvent in Fourier space is just this denominator, this one. Now, the property of the resolvents are very interesting for a very simple reason. The resolvent can have poles, and the poles of the resolvent are complex numbers. Now, in general, if you look at the pole of G is the resolvent. The pole is an energy shift. This is called the lamp shift. And then there is an inverse lifetime. So you see the inverse lifetime, gamma, is proportional to the distance of the pole from the real axis. Therefore, so gamma is what gives you the exponential decay. And delta E is just the lamp shift. If the pole is on the real axis, it does not decay. The system does not decay anymore, because the inverse lifetime becomes infinite. So in a sense, your task is easy. You look for the resolvent. You look at the poles of the resolvent. If the pole, according to the parameters of the theory, the length, the distance, the coupling, whatever, if the pole touches the real axis, the system becomes stable. Okay, so in a way, you just have to understand when the pole can touch the real axis, and then the game is over. Now, there are all the theorems in quantum field theory by Schwinger and by Araki and collaborators. These are theorems of the, well, a theorem in quantum field theory. This is an oxymoron. There is no such a thing like a theorem in quantum field theory. However, I mean, it's a quantum field theoretical theorem. The poles can only be simple poles. You cannot have double poles. And also, Araki used it in a brilliant way to compute the Fermi-Golden rule. Araki and collaborators in 1958. Okay, so this idea, I'm summarizing 20 years of quantum field theory. Just look at the position of the pole. If the pole touches the real axis, the system becomes stable. Okay. Now, I told you before, what happens if you have two atoms and you have a photon, enough energy for the photon to be between the two atoms? I take this, what is called the first excitation sector. So there is either one atom is excited, or the other atom is excited, or there is one photon in the system, nothing else. I cannot have two atoms excited. It's a single excitation sector. Now, for free, if you look at the structure of the bound state, the structure of the bound state is the expression I wrote before, and it's automatically entangled. You see? So the stable state is an entangled state plus a photon and the two atoms in the ground state. So you see, in a sense, you get entangled you get entanglement for free. You set one excitation in the system, you wait, and if the photon is trapped, the system is automatically entangled. You don't have to do anything special in order to entangle the system. Okay, so this is good news. Let me now go to the two excitations. And now I put two photons in the system. And this was interesting for a number of reasons, because the two photons in the system can be emitted this way, or this way, or this way. When they are emitted in the same direction, in a way you are having a photon rectifier. So this was a photon diode, and this was very interesting for applications. Okay, because the two photons are emitted in the same direction. Okay, so we set up the whole machinery of quantum field theory in order to understand whether the two photons can be emitted in the same direction and with which probability. I don't give you the analysis. The analysis is complicated because, unfortunately, the field theory is complicated. You have to renormalize what is called the renormalization of the vertex. And the renormalization of the vector is always cumbersome in field theory. You don't renormalize the state. You have to renormalize the interaction. However, you can do this. You can do this. You have to sum the diagrams in a certain way. It's not a theorem. It's quantum field theoretical technique. So it's the mathematics is sloppy, but it converges. So we know that it is as rigorous as it can be. And when you resum the diagram and renormalize the theory, that's what happens. You can look at the probability that the two photons K1 and K2 be emitted either in opposite directions or in the same direction. Now, this was, as I was telling you, interesting for non-reciprocity and the diode, and we found this beautiful result without understanding it very well. So when you go to the small coupling limit, this ratio becomes 3. Okay, so it's not a diode because you would like to have 100% probability. It's not 100%, but you gain a factor 3. So the probability that the two photons are emitted in the same direction rather than in opposite direction is 3, which is not infinity, but it's something. So we set up, I don't have an understanding of this phenomenon. I tried to understand it in simple terms without renormalizing the vertex and the theory. It was difficult. And eventually, we decided to study the dynamics. And this is the main message I want to give you today. So, of course, the dynamics, this was out of reach with quantum field theory 40 years ago, 30 years ago. It is within reach nowadays because we have quantum techniques. So not quantum computers, but quantum-inspired techniques. And we use tensor networks. So we use tensor networks, and we analyze the dynamics of two atoms initially prepared in an excited state. Both of the atoms are excited, and you look at the emissions. And that's what happens. So you look at the emission, and you get, you see, below I showed you what the scattering looks like. And also, you see, this is the way, what I'm doing here is I'm sending two photons on the two atoms I'm sending one photon from the two different sides on the two atoms, and I'm looking at the formation of the stable state here. Okay, so that's the way the stable state is formed, and then emits the photon. Now, this is interesting from the theoretical point of view. It is very interesting when you try and understand things, because when you form the excited state, this excited state wants to decay. And the way it decays depends on the route in the Hilbert space this system is choosing. And essentially what's happening when you have two photons is that you have the two photons, like in all phenomena of symmetry breaking. One of the photon is emitted. This is random. It can be emitted right or left. Assume that it's emitted right. Then the two atoms must lower from two excitation to one excitation. This one excitation is shared between the two atoms, but with a phase. So it's the phase of the intermediate state that is giving you the correlated emission. And to tell you the truth, I would not be able to understand this without the simulation. I was trying to understand, is there an easy way to explain the phenomenon? Through the simulation, I understood that you emit a photon, this triggers a mechanism, and the intermediate state is a phase that triggers with probability 3, a factor 3, this emission rather than this one. It's the phase of the intermediate state. Okay, having understood this, we went to more atoms. So these are more atoms in a waveguide, but this can be more atoms in your waveguides. I hope to be doing this very soon. And we set up the mechanism, and we looked at the emitted field. Sorry. The name of Rosa should be on the slide. I don't know why it disappeared. This is the poster by Rosa, so it should have been her name there. Sorry. I put it, and maybe I didn't save the file. I'm sorry. So this is the poster outside. So you look at the two excitation sector. You have 4 atoms or 6 atoms, and look at what happens. So you see, there are phenomena in which the photon bounces back and forth between the atoms. Look, these are the positions of the atoms. How do you know that? Because the electric field should vanish there. So this is the stable state. And this is the emitted state. So you see, if you look at this non-Markovian phenomenon, this is the burst. It's it's forerunning the super-radiant burst. So you see, it's 2 photons. It's not super-radiant. There is no super-radiance. It's forerunning the phenomenon. You have 2 photons, and and you look at the emission, and the emission looks like this. You see, depending on a parameter eta. Eta is essentially a parameter which tells you how the system resonates. It's the ratio between lambda and the distance between the 2 atoms at the edge of the cavity, say. Okay, that's what I wanted to tell you. I hope I will be able to tell you more. It is clear that these new techniques for simulating quantum systems based on tensor networks, multi-process states, are extremely efficient, not because they enable you to solve this is beautiful, but because they enable you to capture the mechanism of formation and of formation of the system and of decay. This was unthinkable until maybe no more than 15 years ago. Thank you very much for your attention.
Okay, thank you very much for the talk. Paper is open for questions. So let me start. I wonder, so when I think about 2 atoms in a 1D world, and then in principle you can think about the Dicke model, and if I now say put 2 excitations into these 2 atoms and let them decay, then there's 2 states. One is the subradiant, one is the superradiant state. So I think you don't even need to put 2 excitations. You just excite 1 atom. then you should end up in this long-living state, which in the Dicke language is
A dark
is
state,
the
yeah, in the dark
subradiant
state.
because if the distance between the two so I think you can formally show if the distance between the atoms is lambda half or some lambda integer multiple of lambda more, the Hamiltonian is the Dicke Hamiltonian,
Yeah.
isn't it?
Yeah, it is the Dicke Hamiltonian. The point is that
So
if you want to have correlated emissions, for instance, Nakamura in Japan did something very bright. He biased the system in energy in such a way that he biased the energy he added a term in the Hamiltonian in such a way that the two emissions would be correlated. So the point is that you would like to control the direction of the emissions. And this is outside the Dicke model. The Dicke model, you will break the symmetry.
yeah.
Yes. So you want to be able to, say, inject one photon this way and get two photons this way, or something like that.
Okay.
The comment is correct. Yeah, it's a Dicke system. Yeah.
Okay, thanks. More questions? So people are ready for the coffee break, it seems. So then let's thank both speakers again.
Thank you.